For this video, you're going to need pages 5, 6, 7, 8, and 9. So if you want to go ahead and get yourself organized now, and this is the new numbering from the Parabola PDF in topics. So 5, 6, and then I'm considering this now, page 7, and page 8, and page 9. So if you want to go ahead and get yourself organized, and then I'll start the video. So page 5 is basically a recap, and I'll put this on the class page as well. But the things that are highlighted in yellow, I've already discussed those in previous videos. So I'm going to ask you to refer back to the 2 videos from this week to go ahead and complete all of these. And then there are a few that I would like to go over with you, but you already have all the other answers in your notes, and I would like for you to look at your own notes and fill these things in, and then scan this to me, scan the completed note set to me, and it will all be mapped out on the class page, as I said. But I would like to look at number 4 with you. So the vertex, which we've talked about, also known as the turning point, the vertex is considered a minimum value when the lead coefficient's positive 1 and when the graph is concave up. And I just wanted to make sure that you all understand that. So when the graph is concave up, so the vertex would sit at the bottom and then the curve would go up. This would be a minimum value or a minimum point. And then it's considered a maximum when the lead coefficient's negative, and when A is negative, and when the graph is concave down, then the vertex sits at the top and it's a maximum point. So if I had something, if my vertex occurred in quadrant number 1 and the graph turned down, it would go through the x-axis. So here my vertex would be a maximum point. And the actual value, the max value, is the y-coordinate of the vertex. So the point itself would be considered a maximum, and the actual value, the maximum value of the function, would be the y-coordinate of the vertex. And then the same logic would apply with the minimum. A minimum value, if you were asked for a minimum value, it would be the y-coordinate of the vertex, whatever that is. That would be the minimum or maximum value of the function. But concave up, minimum would be associated with a curve that turns up, a minimum value with the vertex, and then a maximum value would be associated with a concave down when the graph turns down. And then you've got all the answers. You've got access to all of the other answers. And I would like to look at number 9. This is sort of a trick question, so I'm going to go ahead and just explain this to you. The direction of opening does not affect the roots. So this is no. The direction of opening does not affect the roots. The vertex would be different. They would have different vertex. But crossing the x-axis would be the same regardless of direction of opening. And I don't know if we'll have much time to explore that remotely, but that would be the correct response to that. The roots are the same regardless of direction of opening, and the placement of the vertex would, of course, that would be different if it was, concave up, concave down. And let's look at page number 6. So you can answer everything here, and I would like to look at this sketch with you. I would like to look at number 13. First of all, I need to make sure that you have the correct function written in your notes. And I changed this so that it would be a little bit easier for us to work with. So I'm going with f of x equaling x squared plus 5x plus 4. And what you have in your notes may be different, so I just want to make sure that you've got the right function. And remember, f of x and y, same thing. F of x replaces y in that ordered pair. So let's go through the parts together. Here, you're asked for the roots or zeros. And zeros, that's a word that we've not yet talked about. And that is on page, actually I'm going to go to page 7 to define zeros for just a minute. And this is actually what we just did. Number 5, I'm now on page 7. Number 5 on page 7. The vertex is the highest point on the graph. When it's the highest point on the graph, we call that a maximum. And when it's the lowest point on the graph, we call that a minimum. Solutions are also called zeros. And this is a new word, and this is number 7, the response to number 7 on page 7, zeros. Zeros can be thought of as roots, solutions, x-intercepts, all sort of interchangeable for us in Algebra 1. And some of these things will be refined later in a higher level course, but for now, a zero for us would just be synonymous with solution, roots, x-intercept. So solutions to quadratic equations can be called any of the above. So we can call those roots, or we can call them zeros. And when you're referring to something as a zero, it's implied that y itself is 0 since this is an x-intercept. So it would be an ordered pair, whatever value x is, but the y partner would be 0, and thus the name zeros. And I will let you do 9, 10, and 11 on your own. You're just visually looking to determine the number of roots, and then they're asking you for the zeros. And I think I'm just going to let you do that on your own. And now I'm going to go back to page number 6. So I'm going to go back to page number 6. So here I am on page number 6. And then, you can fill these, you can fill the top in by yourself. Let's focus on number 13 together on the video. And let's go through the pertinent pieces here using the formulas and plotting points and kind of analyzing some things together. And let me get the camera focused in just a little bit better. So give it a second. Okay, so here's my function that I'm working with, x squared plus 5x plus 4. And the first thing I'm asked to identify are the roots or the zeros. So in order to do that, I chose something that was really easy. This is factorable, and hopefully it's, hopefully you recognize that I'm looking for factors of 4. That's sum to 5, and that's going to be 4 and 1. So to factor this is just simply going to factor as x plus 4 times x plus 1, and since I'm looking for the roots, I'll set this equal to 0. So that means that my two solutions are -4 and -1. So they serve as my roots or zeros, so that would be the correct response up here. So -4, -1 in the braces, and notice that zeros, it's implied that this would be the ordered pair -4, 0, coupled with the ordered pair -1, 0. So all of this is implied or assumed in the vocabulary, in the terminology right here. So just by the fact that you're stating that it is a root or a zero, you're now assuming that that's associated with the ordered pair where the y coordinate is 0, and thus creating points that would sit directly on the x-axis. Now let's calculate the vertex, or I guess, well, we can go ahead and plot the points. So let's go ahead and plot our roots. So we've got -4, I'm on the x-axis. I've got -4, and I've got -1. And the graph didn't show up that well, but it's okay. We're just going to plot some rough points in and then sketch our curve, and that's going to be sufficient for our purposes here. Let's now move to the vertex, and let's use this formula for the vertex. So I'm going to move over to the vertex. And the vertex for this is a fraction, but I've tried to choose numbers that end up with nice integers, but I actually chose something that have fractions here, but it's not that big of a deal. Let's just go ahead and get through it. The graphing it's sort of approximate, so it doesn't have to be exact, so it's okay. But let's go back. Let's look at this formula. Let me make the camera zoom in a little bit more. So here's my vertex work. And remember, the x-coordinate or the vertex is using the formula -b/2a. And then to find the y partner, it's f of, which is just a fancy way of saying take the x value that you get generated out of this, and we're going to plug that into the quadratic above. And as I said, we're going to get fractions, but it's not really that big of a deal. So here we go, finding the x-coordinate. So I've got my negative sign built into the formula. There's my fraction bar and the 2, and let me customize this to fit. So B in this particular problem is 5, and then A is 1. So that's really all I'm doing. So the x-coordinate for the vertex is the point -5/2, which is the point -2.5. And my vertex is an ordered pair with an x and the y partner. So I'll say my x-coordinate is -5/2, which is going to put me, let's see, here's -2, -2.5, somewhere around in here. Whoops, I'm not on the screen. The x-coordinate, -2, so I'm going to come here between the 2 and the 3, but I need to know how far down to go to plot the point. So that's why I need to calculate the y partner so that I know where to go on the y-axis to plot this point. So let's figure out what the y partner is. And I'm going to take this value, and I'll keep it in its fraction form, and I'm going to slip it into the quadratic, and I am going to get a fraction, but you know, it's not that big of a deal. As I said, I've tried to find numbers that are pretty for the other examples, but it's kind of hard to make all of these nice integral values. So I'm going to evaluate this, and I'll get some scratch paper to do this. So here I have x squared plus 5x plus 4, and my x value is -5/2. So I'm looking for my y coordinate. I'm going to have -5/2, which I'm going to square. That's x squared plus 5 times x, -5/2 plus 4. And when I square this, this is y equals, when I square this, I get positive 25/4, and then that's going to be -25/2 plus 4. And if I give everyone a denominator of 4, then I'm going to have 25/4, and that's going to be multiplying that 50, and then this is going to end up being 16/4. And I've already done all the work in advance, and this turns out to be 9/4. So y is -9/4. Y is -9/4. Just take my word for it on this. And we're not going to do a whole lot of these, but you do need to understand how the process works. So just to recap what I just did, I used this formula to find the x value of the vertex, and I ended up with a fraction. But I now need to find the y partner so that I know where to go to plot the point. I know where the x-coordinate is, but I need to know how far down I should go to plot the y coordinate of the vertex. So in order to find the y partner, I take the x value that I just calculated with my formula, and I go back to my original quadratic, and I let x take on that particular value, and I end up with the fraction -9/4. So my vertex is going to be the ordered pair, -5/2, -9/4. And I'm going to now go back to my graph. So I've got -2.5, and I'm going to come down, let's see, that's 2 1/4. So I'm going to come down just a little bit past 2, and this doesn't have to be extremely exact, so don't get too carried away with it. That's approximate enough for our purposes. So here are my roots or zeros, which I found by factoring. They could have been irrational. That meant I would have had to use the quadratic formula to get irrational roots, and I would just have approximated between the integral values. So as I said, these don't have to be perfect and beautiful. I just want you to have a basic understanding of the shape and how some of the key points on the shape are calculated. And I just want to tie things together so that you understand why we've learned what we've learned this year. Okay, the axis of symmetry. Well, the axis of symmetry would be the line that actually divides the shape, that would split the shape into 2 equal halves. And the axis of symmetry is the vertical line. This is an equation of a line. It's not just referring to the x-coordinate of the vertex. It's the vertical line, x equals -5/2. Because that symmetric line goes directly through the vertex, so the symmetric line would go directly through the vertex, splitting the curve into 2 equal halves. Now, the y-intercept. The y-intercept occurs when x is 0. So when I go back and look at my original quadratic, if I let x become 0, the only number left standing is the constant, or 4. So the y-intercept is the ordered pair 0, 4. to intercept the y-axis, it's assumed or it's implied that the x-coordinate is 0. So when x is 0, the point sits right on the y-axis. So I'm going to now move back to my graph, and I'm going to plot the point 0, 4. And I'm going to, this graph did not photocopy well, so I'm going to go ahead and draw my axis of symmetry and just sort of split this in half a little bit. Oops. So here I'm kind of splitting this in half somewhat. I didn't do a great job with that, but to draw the curve in, I'm just going to take a highlighter and I'm going to connect here. And by plotting that y-intercept, it sort of funnels the curve. It tells you how wide it should be. The y-intercept is equal distance from this axis of symmetry. All the points that occur along the graph are equal distance from the axis of symmetry. So there are traits that you'll explore in higher level courses, but just to give some crude understanding for Algebra 1 purposes, the y-intercept would also have a partner with the same y-coordinate but a different x-coordinate. And I went ahead and figured this out. For this particular curve, for this particular symmetric partner here, this point is 4 is 2.5 units to the right of the symmetric line, which means his partner would be 2.5 units to the left of the symmetric line. So his partner is going to be -5, +4. His symmetric partner, and this is the point 0, 4. The symmetric partner is going to have the same y-coordinate, but it's going to have a different x-coordinate. And the points are generated because they're equal distance from this line, this axis of symmetry that divides the shape into 2 equal halves. Okay, let's move on. Maximum or minimum? Well, here, this is going to be a minimum value because the curve opens up. So the vertex is going to serve as a minimum, and the actual value, as I stated earlier, the value is the y-coordinate of the vertex. So the minimum value for this function would be -9/4. Domain and range, 2 things we haven't talked about since first semester. The domain, remember the domain would be your limit on, or the domain would describe the horizontal spread of the graph. Is there a limit? Is the graph confined horizontally? And it's not, so the domain for the quadratic, for this particular quadratic, the domain would be all real numbers. There's no limit to how wide this can go. So here your domain would be all real numbers. Your range, however, remember the range is describing what's happening to the graph vertically. The range is directly related to the y-coordinate of the vertex. Since the vertex is the minimum at the bottom, this is the least value on this curve. This point is the lowest point and it's the least value on the curve. All of the other y-coordinates on this curve are going to be greater than or equal to -9/4. So the range for this particular quadratic would be all y values greater than or equal to -9/4. So let me zoom out and let's just recap what we just did. So here's our quadratic, and we're looking at some of the critical points in the quadratic, meaning the roots, the vertex, where does it cross the y-axis? Can we describe the axis of symmetry, which is the imaginary line that would divide it into 2 equal shapes? Do we know how to find all of these pieces? And then can we describe if we have a minimum value or a maximum value? And that's determined by direction of opening. And then to find the symmetric partner for the y-intercept, you would just simply count the number of units. The y-intercept would be, you would just count the opposite to the opposite side, the equal distance, the same number of units that you would need to go from the center to get to the y-intercept. You would count the same number of units or boxes on your grid in the opposite direction to get the partner. And I would like to move now to page number 7. I would like for you to do these on your own, and I guess we did talk about this for a few minutes. And I would like for you to do these on your own. We talked about zeros, and let's look at number 8. Let's go to page 8. I would like for you to try a few of these graphs on your own, but I would like to look at number 12 before I end the video. So I'm on page 8, number 12. The graph is already sketched for us. So I want you to look at it. If you need to sketch yours in just a little bit better, go ahead and please do that. And we're asked to identify the axis of symmetry. So I went ahead and drew mine in. This graph clearly crosses the x-axis at 2 and 4. And the axis of symmetry would be directly in the middle of 2 and 4. So the axis of symmetry is going to be the vertical line x equals 3. So the axis of symmetry is the vertical line x equals 3. And I think it's pretty easy to see that the vertex sitting down here, here's my vertex. The vertex is the ordered pair where x is 3 and y is negative 2. So the vertex here is the ordered pair, positive 3, negative 2. How many zeros or roots does this graph have? Well, zeros, we discussed a minute ago, zeros would be the points where it were the spots where it would cross the x-axis. So here I have 2 zeros. And then you're asked to tell, what are the zeros? Well, I'm going to give myself braces to imply a solution set. And my 2 zeros are 2, 4. 2, 4, which is implied that this is the ordered pair 2, 0, and that the other ordered pair is the ordered pair 4, 0. So the zeros or roots occur when y is 0 and you're on the x-axis. These are your x-intercepts, just to tie everything together. The domain, as I said before, the domain for the quadratics would be all real numbers. So your domain would be all reals. And then your range is going to be directly related to the y-coordinate of the vertex. So here the vertex is the minimum, sitting at the bottom. This is the minimum value. And all of the y-coordinates for any ordered pair that sits on this curve, the least y-coordinate is going to be negative 2. So this means that your range for this particular graph is going to be all y values greater than or equal to negative 2. I'm going to stop the video here and ask you to do some of these problems on your own. I'm going to ask you to do a few things on your own on pages 8 and 9.